Measurement mentors I've had over the years, and if you watch the video that was quite popular on the quietest place in the world in measuring it, I think that was at Microsoft.
Yeah.
If you watch it, you'll notice he was there helping set up the setup to measure the quietest place in the
A
world.
little younger though, more hair.
But he also, in 2018, gave what was for me one of the most important presentations I'd seen, which was the introduction of the Brüel and Kjær 5128. He introduced it at Alma, January 2018.
That's right.
First presentation of the morning, and a lot of us there were stunned by what we were seeing when they showed the research and presented what they'd found and what they were going to be doing. I won't give details because there were some very interesting meetings that happened after that. But with that, I'm going to turn it over to Vince. Vince, thanks for coming out.
Thank you, guys. Thank you for being here. I'm going to start just by presenting kind of a little more detail about me. And I'm a French citizen. I moved in the U.S. when I was 26, and I work in the U.S. now for 22 years, mainly in the sound vibration industry. And I joined B&K in 2013, and I felt like I always knew about B&K, always used B&K equipment. In my labs in Paris, we were using B&K mics and stuff like that. So it was a real treat for me to join this great company. But we have a new name now. If you look at the logo on the top right here, it's not B&K anymore, it's HBK. And our mother company, called Spectrus, they own about a dozen companies, decided to merge the two biggest companies they have, Hottinger and Brüel and Kjær. Hottinger is specialized in physical tests, strain gauges measurement, torque measurement, electrical measurement, and obviously we're specialized in sound vibration. So this is a big company. We're talking about 3,000 employees now, and so there's a lot of things going on at the company at the moment. Yeah. Okay, so I just want to give you a quick summary of our journey in the electroacoustic testing. And I could have started this journey, actually in the Second World War when Brüel and Kjær designed their first instrument. The first instrument was an audio analyzer. But I didn't go that far. I started here in 1991, and B&K had a standalone analyzer called 2012. It was pure analog. There's still few analyzers around. If you go to Sean Oliver's lab, he has one. I
think THX does too.
THX may have one too. Yeah. I never used one, but people still believe it was a great analyzer. So this it was standalone, no computers, easy to use. Buttons. And at that time, B&K was very proud of this equipment. We were making everything in the analyzer, even the screws. So. A little later, 2006, B&K introduced a software platform called Lapshop, which was used in the automotive and aerospace industry. That was late 90s. In 2006, we introduced an electroacoustic module in Lapshop, and this is when we designed the SSR analyzer, if you remember, steady state response analyzer. And there's some other good stuff in this analyzer. So if I move up here, in 2017, November 2017, this is when we released the 5128. And June, we mentioned it, we presented, in the year after. But the team in Denmark spent 12 years of R&D working on this Mac. 12 years of R&D. It was absolutely insane. We're talking about 3D imagery, 3D MRI scanners. We've done all this work. And it was an incredible piece of work, and it was a great success too. So it was a great move for us. In December 2017, so a few months later, we introduced an audio interface called the 3670. That was the first time B&K had an audio interface that had an ASO driver open to the world, and it's an 8-in. 2 out, and has all the signal conditioning necessary for powering the ears, powering the microphones, powering the accelerometers, and such like that. A little bit later, we introduced a new software platform called the EA engine, or electroacoustic engine, also called BZ7852. And this is an application that I specialize in. My COVID time, I spend a lot of time with that app. And it's a toolbox, right? It's a toolbox designed for engineers. If you know a little bit of Python, a little bit of MATLAB, a little bit of Visual Studio, you can create your own application, basically. You don't have to reinvent the signal processing. All the DSPs validated and available in this application. And so it was really primarily designed for a production test. But we have customers who are using it in R&D as well. Okay, so here's the presentation today. We're going to talk about a human metric. And I believe we have a good understanding on what to measure and how to measure things. This has been pretty well established over the years. But there's another domain which is probably sometimes very unknown. It's the human domain, how we perceive sound, right? So there's a physical domain and there's human domain. And sometimes we assume that the physical domain correlates with the human domain. Well, most of the time it doesn't. So this is this presentation here. So in the physics domain, we have microphones, we have couplers. We know how to make those for sure. On the human domain, now we have a hats, 5128 hats that represent an average human being. We're using a lot of RMS, decibel values in the physical domain, right? FFTs, RTAs, CPBs, intercom analysis, cross power, coherence. But what's about the human domain? Do you think we have an FFT analyzer built in our brain here? Yes and no, right? Sometimes, yes. Yeah. Well, do you think decibel is a good representation of the sound perception? No, not really. Why are we using it today in 2023? Right?
It's logarithmic, right? So it's like
The logarithmic part definitely matches human perception, but
Yeah,
it's constant low frequency, which humans are not.
exactly. And I'm going to channel the decibel, and we'll see if it works here in this room and with this PA system. But I'll try to change it. And then we have the frequency response function. This ratio between the output over the input, which we always use that one. Now we have the preferred frequency response, so that's kind of interesting. So we can refer to how human preferred, and I think it was pretty well received. And thanks to Channel in this work. THD, THD is the most critical thing. Everyone measures THD, and the problem is, most of the time, when you measure a speaker and you say, well, I measured that speaker, and that speaker has 8% distortion. Can you tell if it's a good speaker or a bad speaker? No. It's impossible. And I'm going to try to show you and to prove it to you. Okay, so challenging the decibel value here, I picked up 6 industrial sound. And you can see from the time domain, they have different amplitudes, clearly. They're not, the amplitude is not similar, obviously. And we're looking at Pascal over time here on top. And the bottom graph is the sonogram. So this is time, this is frequencies, and it's color-coded. So dark colors mean low levels, bright colors mean high levels. So you can see just from the frequency content that they're very different. I'm going to play that again. We do it? Fix it? No?
Is it on the headphone jack?
Yeah, I guess so. Yeah, it was working like a few minutes ago, but it's okay. Headphone. Let me try again here. Okay, let me try to play that again. So I'm going to show you the result in dBA. decibel A-weighted over time. And I'm not cheating here. This is a true analysis here. So for the 6 sounds, basically what we're showing is there's no differences in decibel. Yeah, those sounds have been carefully chosen. Sometimes, you can correlate with human perception. And that, give an example, nothing correlates. So can we rely on decibel all the time? Should we rely on decibel all the time? Should we apply this A-weighting function that everyone uses? Difficult to say, huh? I would say no. All right, so there's another metric called time varying loudness, which is a pretty well-known metric in the automotive and the NVH industry in Detroit. They use it now. It's a very, very standard metric. And the roots of that metric is coming from Germany, Zwickau, University of Munich, where they've done a lot of work. And this metric actually has a lot of good characteristics. And I believe it correlates very well with how we perceive sound. So I'm going to show you the loudness analysis over time of those 6 industrial sounds. Now we start to be able to rank those sounds. The jackhammer was certainly the loudest. You can see that the unit we use for loudness is not the decibel, it's sones. And and this is sones over time here. And this standard, this metric is now in the ISO standard. So it's public to the world, right? Anyone can use it. It's in the ISO 532-1 from 2017. And I would highly recommend to take a look at this. All right, so what's the secret sauce behind this metric? Well, there's a couple things, there's a lot of things actually, but there's a couple things I would like to show you. First of all, that's the metric that integrates the frequency masking of the human ear, right? So have you heard about frequency masking? I guess so, yes. No? Oh, okay, interesting. So let me start by showing you the human threshold in decibel here. And let's pretend that we're going to inject a 1 kilohertz tone at a given amplitude, right? We're crossing this human threshold, so we should be able to hear it. And obviously we're going to have some low orders harmonics, so it's some distortion. But look at what happened when I increase the tone. We have an associated curve with it, called the masking curve, which is showing up here, which is function of the amplitude of that tone. It is also a function of frequency, so it's a little more complicated than it looks like. And this masking curve, basically what happened is, if you generated tones under that masking curve, the human ear will not be able to perceive it. That will be masked, okay? So now if I generated tones that is higher in frequencies and cross this masking curve, you will be able to hear it. So you start to have a feel for why sometimes THD doesn't correlate very well, and sometimes why a rub does, is an important problem in the speaker system. Well, this is why, because of the masking effect of the human ear. Okay, so just to challenge the THD again, if I generate a 1 kilohertz tone, and if I, let's say, generate a 2 kilohertz harmonic, 20 dB below the main tone, if you do the math, you have 10% of distortion right there. 10% of distortion, but you cannot hear it. You won't be able to hear it. You got 10% on one side, and no effect on the perception at all. Now, if you look at harmonic 10, for example, where we have the rub and buzz issues typically, if the harmonic 10 is 46 dB below the main tone, we only have 0.05% distortion, and guess what? We're above the masking curve, we're able to hear it. All right, so this is where the demo gets a little tricky here. And because I'm going to rely on the speaker system, but I just want to hopefully try to play you a tone, actually multiple tones, and one will be masked, and let me explain what I have here on the screen. So I got this sonogram plot. This is time here. This is frequency, and this is decibel here. And I'm going to introduce a very steady tone for the whole sequence here. And it'll have the same amplitude. That'll be my main tone. And I'm going to introduce a second tone here. And I'm going to increase its amplitude such a way that I'm going to be masked at the beginning. And I will cross the masking curve, and we'll be able to hear it. Right? So I'm just amplifying the amplitude of that tone here. And then what I'm going to do here, I'm going to put this tone back under the masking curve. I'm going to sweep in frequencies. And at some point of time, I'm going to cross this masking curve. You'll be able to hear it. And same thing after. I'm bringing back the second tone under the masking curve, and I'm going to sweep down. And then to show you that, we'll have an FFT, 2D FFT representation here. This is a multi-FFT representation. A 2D, so you will be able to see exactly what's going on. And just try to listen to it, and hopefully the speaker doesn't have too much distortion issues and rub and buzz. And normally, you should be able, when the tones is masked, you shouldn't be able to hear it. That's right. I never tried this, so it's going to be interesting. And we're not paying again. Oh, okay. What? No signals? Ah.
Otherwise, it keeps switching.
Yeah. It's not a Mac. No way. It's not a Mac. Full mask. There's a little bit of distortion here. So now we're clearly on the masking curve. This is pretty well masked. Should be masked now. There's some distortion, you can't hear it. Alright. So I have this presentation on YouTube, so I would recommend to use good headphones, and that'll be perfect. But I hope you got a little feel for the masking effect here. So in the loudness analysis, loudness metric, we use what we call a specific loudness. So we're not even talking about frequency anymore, we're talking bark bands. There's 24 bark bands. So those are the bark bands here. And we got time, and we got zones there. And specific loudness will show you exactly what you hear, basically. And we'll show you the masking effect. So I'm going to play that again. And he decided to quit again. I'll blame my computer, I guess. But basically what happened here, you can see this is the spectrum, and at some point we're crossing, and you can see that another bark band was excited there, and you can hear it. And the FFT always shows the peak. That's the FFT will show you everything you need. The specific loudness will show you exactly what you perceive. That's the idea behind it. Question?
All this is on YouTube somewhere?
Yes.
Yeah.
Follow-up question. The main peak in the human neck seems to wobble up and down quite a bit.
Yes.
That does not correlate with what I'm hearing instead. No.
Right.
Repeat the question.
Yeah, there's some wobbling effect here, right?
Yeah,
I mean, the
sound
amplitude.
wave is constant, but on the human vein shows it wobbling up and down.
Yeah.
I'm assuming it's just a calculation thing.
Yes, actually, when you listen to it, when you start to have two tones, there's beating frequencies happening here with some beating sounds and some. You can hear it actually, not maybe here, but again, I would refer to the YouTube video.
It's more noticeable the closer the two tones get together.
Exactly. Exactly. That's the effect on an airplane, right? You have two engines running at more or less the same rotation speed, but they're not exactly the same rotation speed, and you get this effect. So the specific loudness will show you that actually. It's very sensitive to that actually. So what's about rub and buzz here? I had a good colleague He's works for B&K for many, many years. He's in Michigan. And he had two speakers, a good one and a bad one. They're exactly the same. And he measured rev and buzz one day. So the good speaker here, we had a 6% distortion, which was quite high actually, but is considered a good speaker. And the bad speaker, had a distortion of 2% only. It's a bad speaker. Do you see what's going on here? Can someone explain the group?
We're seeing a lot more energy at higher orders.
Correct. Yeah. You see that
Sure, significantly more audible.
those harmonic here are basically present, and they're not present here in the top graph. And those high harmonics are not masked by the main tone, and you can hear it. So a 2% speaker, 2% distortion speaker, can be bad. 8% can be good. So the frequency masking is very well established. It's in the ISO standard, as I mentioned. Everyone knows about it, or at least it's public information. And there's also a time masking happening, right? So it's not just in the frequency masking that we have this effect. It can be also in time masking. I've got this recording here of two sound events. There's one with random noise, and there's a little click. So basically, if I would play that, it would be shh, shh, shh. So there's a little click at the end. And when there's enough time between the two events here, when you process that in the non-stationary loudness, the non-stationary loudness will tell you, hey, we can hear the click. It's not masked. If you have the click close to the random noise signal, now the click is here, right? It's absolutely masked by this main event here, right? So it's a little complicated, It's not just the frequency masking. We're also talking about time masking, and this is where the time varying loudness is very powerful because it integrates both masking. Okay, so in the physics, we have Pascals, and I would love to have a lot of people using more and more Sones, in the human domain, because that at least you will correlate a little bit better with your measurements. I believe so, this metric is a little more solid. Okay, so that was just the introduction of that special metric, and I'd like to introduce you one of my colleagues, one of my incredible brightest engineers he's a doctor actually at B&K, Dr. Sone. And this guy is involved in sound quality, in noise mapping, near field holography, and he's a great colleague of ours here. And he designed an app which is in MATLAB for now, which does BSR, buzz, squeak, and rattle, right? And he fully used the time varying loudness as a metric. So let me explain you the concept here. So the idea there is to test the speaker, right? Test the audio artifacts of the speaker. So the first thing is you can generate a stimulus, a lock sweep to the speaker. You can measure the response. And the algorithm will take the full measured time signal and feed that to a time varying loudness. And we're going to call that curve NY. Okay, so that will contain the linear response and the nonlinear response of the speaker. The algorithm will take another branch here, another turn, and we'll do a linear deconvolution. And so we're going to extract the linear response of the speaker, and we'll feed that linear response in a time varying loudness. Same thing. We're going to call this curve NX. We have NY and NX. If there's no issues, if the speaker is perfectly linear, NY and NX should be, you could superimpose them. That's kind of simple to imagine that. If there's any issues, NY will be greater than NX. So the idea of the metric is to use time varying loudness and make a difference between NY and NX. And the difference basically will tell us if you can perceive the issue or not perceive the issue. Simple as that. Okay, so let me take a quick example here. So I'm using a B&K 4227A artificial mount. It's a speaker, it's pretty well known to have low distortion. I put a microphone in front of that mouth, and I'm going to generate a lock sweep to that mouth, and I'm going to measure the response. And here's the MATLAB app here. And after the sweep is generated and we measure it, we have this result here. So we have the NX and NY curve showing up here on the same diagram. And the bottom diagram shows the difference between the two. The BSR metric is just an average of the difference. So you can specify where you want to start your average, where you want to stop your average, and we'll calculate the average difference, and we'll put it in this number there. Okay, so this speaker 0.4 Sones difference, you cannot hear anything, right? It's close to zero, basically. What I did then after that, I put a piece of tape to generate issues, rattles, and I regenerate that lock sweep again and measure the response. And now you can see at some frequencies the tape is rattling pretty well here, and I can see some differences between NY and NX. The difference shows it's very clear. And I've got a BSR metric and a score of 8 Sones. I can hear that. It's very obvious. So this is kind of the idea there of this metric, using a time varying loudness, very good metric to begin with that correlates with my perception, and we're making some differences between the full response and the linear response of the speaker. Yeah, for people who like to are familiar with the multi-spectrum FFTs, you can see the effect of the tape here, right? The problem is, the FFT will show you this, but can you hear the issue? Can you perceive the issue? That's the key, right? Okay. Same thing, another application. You can certainly use it for testing speakers in a car. I put microphones here at the driver's ear head position. I tested each speakers in my little old Japanese cars that is full of issues. And the front left speakers shows a greater difference. And I knew that there was a panel that was migrating it, and the BSR metric captured that. Okay, so far it's quite simple, but here's what I like about this metric: is now we can use music as a stimulus and estimate how people perceive distortion using music. We're not using a sine sweep anymore. You can still do that. But you can feed the system with some music. Even speech will work very, very well. And the algorithm basically, there's two branches again, same concept. There's the full response. We feed the full response in the time varying loudness. So this one contains all the audio artifacts. And here, we're doing a circular deconvolution and a convolution with the input signal. So basically at this point, we're extracting the linear response from this audio response here. So at this point here, I just filtered just the linear part. And I'm feeding back in the time varying loudness, and we're making a difference. So that's kind of interesting because most of the time we use sine sweep for testing equipment, but now we have a real scenario using music as a stimulus. And here's the issue. This is an iPhone here. I have an iPhone XR, version 10 here, which actually has pretty good distortion performance. If you test it, it's pretty decent. But now when you play certain music track, the micro speakers on that phone will not handle it well. And there's a famous audio track we use in the Silicon Valley called Chord Left. It's a piano track, very muddy. And if the speaker doesn't perform well, you will hear it. It's going to be very obvious. So I'm not sure if I will be able to play the sound again, but I can try.
Recycle back to headphones.
Oh man. Yeah, maybe. Let's try again. No, it's just a piano track. You can download it, and play it on your phone. You'll see what I mean by that. Here's the original sound. So it's a piano track again. You can see the frequency content, and here's the full response measured by the microphones at a certain distance. And you can see from an FFT perspective, there's a lot of differences. They try to enhance the signal, you know, but there's a lot of distortion happening. And when you feed that into the BSR analyzer, you know, clearly the NY curve and the NX curve varies quite a bit. And you know, clearly this one was not very well designed for handling this type, or the micro speaker was not very well designed to play music for sure. So this is kind of you know, one application here. Let me try to play it on my phone maybe. Do that. You know, it'll be live. Just bear with me here for a second if I can. Yeah? Want to make it? Does it work? Did you hear it? Yeah? So I mean, if you play the music on a good set of headphones or speaker, the music is clean, right? But you play that via micro speakers, and micro speakers will have a hard time to handle that. Okay. So this is kind of the idea there. Also, the you know, application will generate impulse responses, and also you can we're able to export also what we call the residual, just the nonlinear part. So you can listen to the nonlinear part of the signal. All right. Any questions? Any questions? Yes.
Hi, could you tell us, so 2 questions, could you tell us a bit more about what you mean by the linear and the non-linear part? And also, how does your algorithm differ from existing approaches like delta wave, for example?
Yeah, I'm not familiar with delta wave, so I cannot answer the question, but I would imagine, is it a difference in the time domain or the type of things?
It's frequency domain, but it's also masking effects built in.
Okay. I'm not familiar with that metric. But really, what we like to do is, you know, if a speaker was perfectly linear, right? You play music through it, you know, you shouldn't have any audio artifacts associated with it. No distortion. You know, it should, what you inputting is what you get, you know, as for an output. But obviously, the nonlinear part will add some frequencies, some issues, and this is the nonlinear part.
Oh, sure. So after measuring the distortion through different speakers, you know, you have this resultant graph. Could that be then fed back and used as a form of EQ to sort of flatten out that frequency response? I sense this is a bit of an issue already. So.
Yeah. That's. Can you fix distortion? You know, that's the problem. That's what you're asking, right? I mean, can you really?
Well, we have this insight now into, okay, this is the actual effect on perception, and it seems like that could lead to at least some EQ or improvement. That's predicted.
Yeah, I'm not sure if you can really filter distortion with an EQ. Usually, it's distortion is distortion, right? You can, it's you know, it's very difficult.
So when we think of EQing, we're thinking linearly changing amplitude. Distortion's a nonlinear effect. So
Distortion comes from the overtone series, right?
correct. So so you'd have to say, okay, I've got a 1 kilohertz signal. Now I've got to reduce something that's at 2, 3, 4, but there's other content there. Some of that content you want. It can't distinguish between what's desired and what isn't.
Got it, okay.
Difficult problem to resolve.
I guess just as like a main idea, kind of summary, if I'm understanding the context. So like a BSR score, you're saying like kind of 0 is ideal, and then going up from there is worse. So the overall kind of presentation is like BSR score is reflective of distortion we can't hear because it's not being masked.
Correct. Yes, yes, absolutely, absolutely. When you get a score of 0, that means there's no issues. You know. Now, what's would be interesting also is to get a mass, right? A score between 1 and 5 would be kind of interesting. But that's something we're working on right now, and give a simpler way to analyze the data and conclude on the data. Right? But yeah, that's kind of the concept here. If there's no difference between the NY curve and the NX curve here, a score of 0 would means it's perfect speaker basically, perfect audio reproduction. 8 sones. I'm clear you can hear that on my phone here. This was not very good.
So you're gonna correlate this to like Moss scoring with like jury testing, mean opinion score.
Yeah, that's the plan.
Okay.
That's the plan. But it will take a lot of time.
Yeah.
So HBK, I think will use a specialized company for doing that.
I couldn't quite see on your scale of your graph, so this might be an obvious answer, but if you did have a perfect speaker on a graph, would it have been a flat line down at the bottom, or is it always your ideal one that you had shown slope down? So I just didn't know what like a perfect theoretical graph would look like.
Yeah. Let me try and find a slide here. Yeah, it's kind of interesting because I say perfect speaker, right? I'm not saying that it's a perfect frequency response. That it's up to you or up to your, What I'm saying is a perfect speaker have known, let's say if we're talking about distortion, has no distortion. Right? So basically, when you have no distortion, basically, this is in Sones here. Again, I would refer to the YouTube videos. You'll have more easier way to visualize that. But basically, if you make the difference between those two curves, here's the difference over time, and here's the amplitude, and it looks like it's auto scaled here. So it looks like a lot of issues, but it's just a scaling effect. Yeah.
Vince, can you go back to the impulse response?
Oh, the impulse response?
Yeah.
So that was the last slide?
There's one of them, yeah.
This one, right?
Okay. All right. That's like a derived impulse response. The way we do it with
Yeah. Yeah, but using non-sweep circular deconvolution.
Oh, okay.
So it's a different animal, but it's
All right. Still derived.
it's not Fahrenheit. It's not the traditional Fahrenheit. All right. Any other questions? It's lunchtime here. I can feel it too. I can hear it too.
Please join us in thanking Vince.
Thank you guys.